Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll define modulus of rigidity and later obtain a relationship between modulus of rigidity, Young's modulus and Poisson's ratio. Now, we have studied Hooke's law for normal stress. So, Hooke's law for normal stress states that normal stress is directly proportional to normal strain within the elastic limit, and the proportionality constant is Young's modulus of elasticity. So, similar law exists for shearing stress, and this Hooke's law for shearing stress states that shear stress is directly proportional to shear strain within the elastic limit. So shear stress is directly proportional to shear strain, or the proportionality constant is G, which is known as rigidity modulus or modulus of rigidity. And you can rearrange the equation and write modulus of rigidity as tau by phi. So from Hooke's law for shearing stress, you will get modulus of rigidity as a ratio of shear stress to shear strain. This ratio will be equal to modulus of rigidity if loading is within the elastic limit. So you can define modulus of rigidity as a ratio of shear stress to shear strain within the elastic limit of the material. So this modulus of rigidity is a property of the material, and it is going to be a constant, and its unit is Newton per mm square or megapascal, or you can even express it in gigapascal. Since shear strain has no unit, and the unit of modulus of rigidity is the unit of shear stress. Now let us establish a relationship between Young's modulus of elasticity, modulus of rigidity and Poisson's ratio. Now consider a square block having side length A. Okay, so the height is A and this distance is A, and fixed at the bottom and subjected to a shearing stress at the top. So when it is subjected to force like this, a shear stress means you have to apply a force acting per unit area on the top surface or on the horizontal plane. This is shear stress. So the force is acting towards left on this top face. Okay. So correspondingly there will be a force acting towards right at the fixed end. Fixed end will exert a force towards right. That will act like this. So any plane if you take, there will be like opposing force. So shear stress is two parallel forces which is trying to shear the block, shear the material. Now this fixed end will exert a rightward force which will be acting towards right. So that is shear stress acting on the horizontal plane. Now this fixed end will also exert a reaction. This reaction, because of this force, this block will be trying to rotate in the anti-clockwise direction. That will try to lift the block from here and press the block downward. So when the block tries to lift from here, there will be a downward force acting here. The fixed end will exert a pull in the downward direction. When it tries to rotate in the anti-clockwise direction, it presses downward on this portion. So this, when it is pressed down, this will exert a reaction, and that reaction will be upward. The fixed end, the surface will exert a force upward, so that force will act upward. So there will be forces acting in the downward direction here and upward direction here. So fixed end is also exerting a reaction in the vertical direction. So here it will be exerting a pull, and here it will be exerting a push. So what I wanted to say is forces are induced like this, and as a result of this shear stress, there will be a shear stress induced on mutually perpendicular plane, and this is known as complementary shear stress. So it is Shear stress cannot exist in a plane alone. It is always associated with the shear stress of equal magnitude on mutually perpendicular planes. This is to balance the block. If shear stress of magnitude tau is acting on a horizontal plane, it will be always associated with the equal magnitude of shear stress on a mutually perpendicular plane, that means vertical plane. So this tau acting will produce a counterclockwise rotation for this block, and this stress will balance and produce a clockwise rotation. So for equilibrium there will be always shear stresses on mutually perpendicular plane, and this is the theorem of complementary shear stress. So you remember that shear stress acting on a plane is always associated with the shear stress on mutually perpendicular plane. So element will be subjected to stresses like this, or any element for that matter within the block will be subjected to stresses like this. Okay, so let us consider the deformation of the block. When subjected to shear stress like this, the block deforms like this, and A moves to A1, B moves to B1, and DC will remain stationary because it is fixed. So this diagonal AC will deform, and it increases its length. Okay. So it is increased length is A1C, and the diagonal BD, it's actually getting shortened. So this was the initial length, and it has reduced because B has moved to B1, it has reduced. So one of the diagonal is getting increased, and the other diagonal, perpendicular diagonal, is getting reduced. So in fact, when it is subjected to stresses like this, if it is pushed like this diagonal will elongate. If it is pushed in the opposite direction, the BD will elongate. Okay. So in this direction, when stress is applied, the diagonal AC will elongate, and the length of the diagonal will increase, and perpendicular diagonal BD will decrease in length. So this decrease is because of a compressive force acting on the diagonal, compressive stress induced on the diagonal, and this increase in length along the diagonal AC is because of a tensile stress acting along that diagonal. So what I wanted to say is, when pure shear stress like this, when it acts on an element, this one of the diagonal will be subjected to tensile stress of magnitude tau, and another diagonal BD will be subjected to same magnitude compressive stress, and this will be proved later in when you study the principal stresses topic. So one of the diagonal is getting stretched, and the stress acting along the diagonal will be tau, stress will be tau, and another diagonal BD, opposite diagonal, compressive stress will be acting, and its magnitude will be equal to tau. So that is what I have shown here. A small element I have taken along this diagonal AC, stress acting, normal stress acting is tau, and perpendicular diagonal there is a compressive stress. So that particular element I have shown here. So along AC there is a tensile stress of magnitude tau, and perpendicular diagonal you have a compressive stress of magnitude tau. Now I just rotated the element and shown like this. AC I put horizontal for easy understanding. I just place the element like this. Now along AC there is a tensile stress, and along BD there is a compressive stress. We can take it as x-axis and y-axis, and we have already studied to find out the strain along x direction. When it is subjected to three-dimensional state of stress, the strain induced is given by Ex in along x direction. It is sigma x by E minus nu sigma y by E minus nu sigma z by E. So along x direction you have stress tau. So sigma x is tau, and y direction, since it is compressive, you have to take minus tau. So sigma y is minus tau, and z direction there is no load, So sigma z is 0. So this term is 0, sigma y is minus tau, sigma x is tau. So you get tau by E minus nu into sigma y is minus tau. So you get tau by E plus nu tau by E, or you can write it as tau by E into 1 plus nu. So that is strain along x direction or along AC, or along this diagonal. So much strain is induced, tau by E plus nu tau by E. That means because of this stretching coming, the AC diagonal AC is getting stretched, positive strain, and because of this compressive stress coming along BD, it is also getting stretched, positive strain only it's coming, because compression will try to elongate AC. So this part is lateral strain induced by this compressive stress is also positive, or it is trying to elongate AC. So you have strain along AC. This is obtained from the stress and Young's modulus. You can get strain along AC. So this let us take as one of the equation to find out the strain along the diagonal AC. So strain along the diagonal AC we are getting from the known stress and Young's modulus of the material. And you can also find out the strain along AC from this geometry. Okay, so this angle is 45 degree. This angle, because it's a square, so this angle is 45 degree. Even after deformation, this movement is very small. Even after deformation, you can take this angle almost equal to 45 degree. Okay, actually the angle will reduce, but that reduction is very small, and you can once again consider this angle as 45 degree. So let us go to the next slide. So this angle is taken as 45. As a result of this shear stress, element deforms into this shape, and deform diagonal is A1C. I am dropping a perpendicular to the deformed diagonal. Okay. A2 is a perpendicular drop to the deformed diagonal A1C. As a result of stresses induced in the diagonal AC and BD, the strain on the diagonal AC is strain on the diagonal AC. We have already got this EAC as tau by E into 1 plus nu. So this I explained in the previous slide. So strain on the diagonal AC is tau by E into 1 plus nu. So this as a result of tensile stress induced on diagonal AC and compressive stress induced on diagonal BD, you are getting a strain on the diagonal AC as tau by E into 1 plus nu. So this is one of the equation. Now let us consider the geometry. Now you can also find out the strain on the diagonal AC as A1C, that is after deformation the length is A1C, and before deformation the length is AC. So A1C minus AC, that is increasing length divided by initial length. So that is strain, increasing length or change in length divided by original length. Instead of AC, you can take it as approximately equal to A2C. I am just dropping a perpendicular to this. So this length and this length is almost same, because this is very small movement. AC and A2C can be taken almost equal. So AC I replaced by A2C. So this length and A2C are taken equal. So these lengths are equal. So A1C minus A2C, we will get A1A2. So instead of A1C minus A2C, A1C minus A2C will get A1A2. So A1C minus A2C are written as A1A2. So you get A1A2 by AC. Now let us go to this triangle A1A2. This angle is approximately equal to 45. So you can write A1A2 as AA1 cos of this angle that is AA1A2, and this angle as I mentioned, this is approximately equal to 45, so you can take this AA1 cos 45. this is adjacent side, A1 A2 divided by AA1 is cos 45. So A1 A2 is AA1 cos 45. Now AA1 cos 45 is 1 by root 2. So AA1 by root 2. So A1 A2 is AA1 by root 2. A1 A2 you can write it as AA1 by root 2. So in this equation A1 A2 I am writing as AA1 by root 2. So you get AA1 I am writing A1 A2 as AA1 by root 2, and again AC is there. So AA1 root 2 AC. Now AA1 from this triangle you can get AA1 by AD is 5 or tan 5. So AA1 you can write it as AD5. Okay. So it's AA1 by root 2 AC. So AA1 by AD is equal to tan 5, or this can be written as 5 because 5 is very small and 5 is a shear strain. So you can write AA1 as AD into 5. So I written as AD into 5 divided by root 2 AC. This is because 5 is AA1 by AD. Now AD the height it is A. So it is AD is A, and even AC so diagonal of a square having side length A is root 2A. So AC is root 2A, AD is A, so A root 2A. So I just replaced AD as A and AC as root 2A. So you get this as A cancels 5 by root 2 into root 2, 5 by 2. So it is 5 divided by 2. So you are getting the strain on the diagonal as 5 by 2. So it's a linear strain on the diagonal AC equal to the shear strain by 2. 5 is a shear strain divided by 2. Now we already obtained a relation for EAC, and you can, so that is in the equation 1, strain on the diagonal is tau by E into 1 plus nu. Already we know it is tau by E into 1 plus nu. So we know strain on the diagonal is equal to tau by E into 1 plus nu. It is also equal to 5 by 2. So combining equation 1 and 3, we can write this tau by E into 1 plus nu is equal to 5 by 2. Now we can rearrange this in tau by 5 is equal to G, modulus of rigidity. Tau by 5, shear stress by shear strain, is modulus of rigidity. You can write E is equal to, I am taking E here, okay, 5 here. Tau by 5 is G, and 2 if you take 2G into 1 plus nu is equal to E. So E is equal to 2G into 1 plus nu, because tau by 5 is G within the elastic limit, or which is modulus of rigidity. So you get E as 2G into 1 plus nu. So Young's modulus is 2G into 1 plus nu, where G is the modulus of rigidity and nu is a Poisson's ratio. So this is a relation between Young's modulus, modulus of rigidity, and Poisson's ratio. Now if you know the Young's modulus and Poisson's ratio of a material, you can find out the modulus of rigidity using this expression. So you can write G is equal to E by 2 into 1 plus nu. So once you know the Young's modulus, you can find out the modulus of rigidity and bulk modulus, provided you know the Poisson's ratio of the material. And Young's modulus, modulus of rigidity, and bulk modulus, they are known as elastic constants. So that's all for today, and thank you for watching.